Okay, we're continuing with Chapter 2 in the Geometry textbook. In this video, we're going to go through Section 2.5, which you can see is on convex polygons. Now, this section is titled Convex Polygons, but we're also going to, in the process, going to be learning about concave polygons and regular polygons, and also polygrams. All right. Definition: a polygon is a closed plane figure whose sides are line segments that intersect only at the endpoints. Okay, so let's make sure we understand this definition. First of all, it's a plane figure, so it's contained within a plane. Well, every figure that we've worked with so far has been a planar figure, and the majority that we're going to work with in this entire course are going to be planar figures. Okay, but this planar figure has sides that are line segments. Okay, but also this plane figure is closed. Closed plane figure whose sides are line segments that intersect only at the endpoints. So this meets all of the characteristics of the triangle. A triangle is this planar figure. Okay, it's closed, meaning like, so a line segment can't be closed. It doesn't have enough dimension to think about it, the idea of it being closed. An angle is not closed. An angle would be open, right? An angle being the union of two rays that share a common endpoint. That's an open figure, an open planar figure. Okay, but a triangle was a closed planar figure. It has enough dimensions. It's two-dimensional. It has enough dimensions to think about the idea of it being open or closed. It was closed. Okay, and it has sides that are line segments, right? And these line segments intersect only at the endpoints. So, you know, it wasn't like we had something like this. Maybe I would say that's closed. It kind of has two sections, but overall it's closed. But the line segments don't intersect, only at the endpoints. Here's another intersection, right? So it's this closed planar figure whose sides are line segments. So you could have a closed planar figure that doesn't have, maybe only one side is a line segment, something like that. But the sides of this closed planar figure don't have sides that are line segments. So it has sides that are line segments, and these line segments intersect only at the endpoints. That's a polygon. That's what a polygon is. Okay? And so a triangle definitely is a polygon. But we can think about drawing another figure that meets this criteria that isn't a triangle, right? There's a closed planar figure with sides that are line segments, where all the line segments, they only intersect at the endpoints. And that's not a triangle. So we see that triangles are a subset of polygons. Okay. Now, one thing to notice is that the title of this section is Convex Polygons. So it looks like we're mainly going to be focusing on a certain category of polygons, a certain subset of polygons. So it's probably going to be the case that you can think about that triangles are going to be a subset of convex polygons. Maybe a triangle is a convex polygon. Let's see. Most polygons considered in this textbook are convex, where the angle measures of convex polygons are between 0 and 180 degrees. So by the angle measures, we can see that they're talking about like the interior angles. So we know the interior angles of a triangle are all between 0 and 180 degrees, right? And that's what they're saying a convex polygon is. So a triangle is a convex polygon is what they're saying. And we can see, though, that the idea of, I guess, a concave polygon would be that it has angles that are reflex angles greater than 180. Okay, so some convex polygons are shown in figure 2.28. Those in figure 2.29 are concave. Okay, so here's some convex polygons. There's the triangle. And we can see that all of the interior angles of these polygons are between 0 and 180. Okay, but now here's an example of concave polygons. Okay, and so, yeah, we can see that in concave polygons, there are some interior angles that are reflex angles that are greater than 180, right? Look, this angle here, the interior angle. There's at least one interior angle in a concave polygon that's greater than 180. That's more than a straight line. Same thing here. Well, no, that's obtuse, but this, or is that? Yeah, that's obtuse. But this would be reflex because it's past the straight line. It's more than 180, you see? Okay, a line segment joining 2 points of a concave polygon can contain points in the exterior of the polygon. Thus, a concave polygon always has at least one reflex angle. Figure 2.30 shows some figures that aren't polygons at all. Okay, yeah, so that's another characteristic that with a concave polygon, you're able to pick 2 points inside of the polygon, draw a line between them, and that line goes outside of the polygon. But you can't do that with a convex polygon. There's no way to do that. And that's because of the reflex angle. Okay, now why aren't these polygons? Well, okay, this is a curved side. This is closed. This is planar, but it's a curved side. It's not a polygon. Here, this is planar. It's got all straight sides, but it's not closed. Here, there's no straight sides. This is closed, planar, but no straight sides. All right, so now you can categorize polygons by their number of sides. So, okay, triangle, quadrilateral, pentagon, hexagon, heptagon, octagon, nonagon, decagon. Okay, but just note, though, that these names refer to both convex and concave polygons. So this would be a 1, 2, 3, 4, 5, 6. This would be a concave hexagon. Now, a triangle can't be concave because it doesn't have enough sides. We know that it's not possible to have a triangle with a reflex angle for an interior angle. So not any of these can be convex or concave, but like in general, you would call this a concave hexagon. This is a hexagon. So I'm not even sure if can you have a concave quadrilateral? I guess you could. Yeah, so there you go. There's a concave quadrilateral. That was what this is. 1, 2, 3, 4. Yeah, okay. Once you get above the 3 sides, you can have concave or convex polygons. All right, with Venn diagrams, the set of all objects under consideration is called the universe. If P, which is the set of all polygons, is the universe, then we could describe the sets T, which are triangles, Q, quadrilaterals, as subsets that lie within the universe P. Sets T and Q are described as disjoint because they have no elements in common. Yeah, so a subset, if you think about it, it's saying that if you're a subset of something, then so triangles are a subset of polygons. Every triangle is a polygon. Every single triangle is a polygon. Every single quadrilateral is a polygon. But since those two are completely separate within the set P of all polygons, then you call that disjoint. Those two sets are disjoint. Okay. Diagonals of a polygon. A diagonal of a polygon is a line segment that joins two non-consecutive vertices. Okay. So it's not just any vertices. This is not a diagonal of this polygon. it's got to be a line segment that's joining. It's got to be a line segment, not just like not a curved line or anything. A line segment that joins non-consecutive vertices. And so you can have a diagonal in any polygon except for triangles, because if you think about it, there's no way to join. There's no non-consecutive vertices, because this is consecutive with this, but it's also consecutive with this. So if you try and skip this and go to this one, but they're consecutive as well. You can't draw a diagonal in a triangle, but everything else you can. Now, if we come back up here, can we draw diagonals in concave polygons? Yes. There's a diagonal. Let's see. There's a diagonal. There's a diagonal. There's a diagonal, right? You do the same thing over here. And just FYI, this would be a diagonal as well. Even though it goes outside of the polygon, it's still, if you think about the definition, it's just saying that it's any line segment that joins non-consecutive vertices of a polygon. It doesn't say anything about it has to stay on the interior of the polygon. So this is a diagonal as well. Okay. Figure 2.32 shows heptagon A, B, C, D, E, F, G, so 7 sides, for which angle GAB, angle B, and angle BCD are some of the interior angles. So angle, let's see, GAB, angle B, and angle BCD are some of the interior angles, and angles 1, 2, and 3 are some of the exterior angles. So yeah, we can think about the idea of what an exterior angle would be is going to be a natural extension of what we learned it to be with triangles. You're just going to do virtual extensions of sides of the polygon, and then if any angle that has one of its sides that is the side of the polygon and the other side is the virtual extension, that's going to be an exterior angle. But like here, this wouldn't be an exterior angle, because both of its sides are virtual extensions. It has to have one of its sides be a side of the polygon, and then the other side be the virtual extension. If both of its sides are the sides of the polygon, so like here, right, that's an interior angle. I mean, this isn't an interior angle. This is just because you drew a diagonal in here. So angles 1, 2, and 3 are some of the exterior angles. You see, virtual extension, one side is the polygon. Virtual extension, one side is the polygon. Virtual extension of a side, one side is the polygon. Because they join consecutive vertices, segments A, B, B, C, and C, D are some of the sides of the heptagon. Yeah, right. Because a diagonal joins non-consecutive vertices of the heptagon, then AC, AD, and AE are among the many diagonals of the polygon. Yeah, these are diagonals. Table 2.4 illustrates selected polygons by number of sides and the corresponding total number of diagonals for each type. So that's something to think about, that how many total diagonals does each type of polygon have? Okay, so as we talked about, a triangle has none, no diagonals. 3 sides, no diagonals. Quadrilateral will have 2 diagonals, 4 sides. Pentagon, 5 sides, 5 diagonals. Hexagon, 6 sides, 9 diagonals. Okay. When the number of sides of a polygon is small, we can list all diagonals by name. For pentagon A, B, C, D, E of table 2.4, we see diagonals AC, AD, BD, BE, and CE, a total of 5. So yeah, AC, AD, AE, BD, BE, right? Just list the non-consecutive letters. Let me make sure I got that right. AC, AD, AE, BD, BE, and then CE. Or no, wait. No, because A and E are consecutive. So let me try again. a CAD, not AE, okay, then BDBE, and then CE. Okay. But so if the polygon is small enough, you can kind of just visually inspect the letter order of the polygon and see how many diagonals there are. But as the number of sides increases, it becomes more difficult to count all the diagonals. In such a case, the formula of this upcoming theorem is most convenient to use. Although this theorem is given without proof, exercise 39 of this section provides some insight for the proof. Okay. Theorem: the total number of diagonals, D, in a polygon of n sides is given by the formula. So D is equal to n times n minus 3 divided by 2. Okay, so, but now notice though, we're still just talking about polygons. I'm not sure why they titled this section convex polygons. This applies to concave polygons as well. Okay, so this is any polygon. And but with a concave polygon, we include this as a diagonal. So here this would have 1, 2, 2. Yeah, a quadrilateral has 2 diagonals because you take, so number of sides 4 times the number of sides minus 3 divided by 2. So that's 4 divided by 2. That's 2 diagonals. Okay, theorem 2.5.1 reaffirms the fact that a triangle has no diagonals. When n is equal to 3, d is equal to 0. Okay. Find the number of diagonals for any pentagon. That's part A, and then part B, the type of polygon that has 9 diagonals. That's a nonagon. Okay, well, a pentagon has 5 sides, so 5 times 5 minus 3 divided by 2. 5 minus 3 is 2. So 5 diagonals in a pentagon. Okay, what about a nonagon? That's 9 sides, so 9 times 9 minus 3 divided by 2. So 9 times 6 divided by 2 would be 27. Oh, wait, no, okay, I read that wrong. They're saying the type of polygon that has 9 diagonals, not 9 sides. So we don't know. We want to find, we first found the number of diagonals for any pentagon. Now we want to figure out what type of polygon has 9 diagonals. So, okay, we want to do this. Solve for n. So, okay, cross multiplying, you get n times n minus 3 is equal to 18. So n squared minus 3n is equal to 18. N squared minus 3n minus 18 is equal to 0. So 6 times 3 is 18. Minus 6 plus 3, okay. Well, n's not going to be minus 3, so n is going to be 6. So this is the hexagon. The hexagon has 9 diagonals. Okay. Sum of the interior angles of a polygon. The following theorem provides the formula for the sum of the interior angles of any polygon. Okay. The sum S of the measures of the interior angles of a polygon with n sides is given by, so S is equal to n minus 2 times 180 degrees, and then note that n is going to have to be greater than 2 for any polygon. The lowest number of sides you can have for a polygon is going to be 3. You can't, with 2 lines, you can't make a closed figure. Okay. So we did in the previous section, the example problems, we did work, I think we found the sum of the interior angles of a quadrilateral. And so we got a sense for how this theorem is developed. Because, okay, let's keep reading. Let us consider an informal proof of this theorem for the special case of a pentagon. Yeah, we did this for a quadrilateral. The proof would change for a polygon of a different number of sides, but only by the number of triangles into which the polygon can be separated. Okay, although this theorem is also true for concave polygons, we consider the proof only for the case of convex polygons. So yeah, let's keep that in mind. We're still talking about, we haven't, whenever they say polygon in this section, they're talking about convex and concave polygons. Okay, so this is the second theorem we've looked at. The first theorem was determining the number of diagonals for a polygon. That's for convex and concave, and same thing here. Again, I don't know why they titled this section convex polygons. I get they're more commonly used, but still. And so the idea is that they're going to use diagonals to separate the polygon into separate triangles. That was the idea of what we did when we proved that the sum of the interior angles of the quadrilateral were 360. We needed one diagonal to separate it into two triangles. So like here, there's more diagonals for a this is a pentagon. There's more diagonals, right? Here's a diagonal, but we don't want to create unnecessary triangles for this proof. We're just trying to separate it into distinct separate triangles. So you just need two diagonals to do that. So okay, let's see. The equations that follow are based upon the sum of the interior angles in triangles ABC, ACD, and ADE. Yeah, all you're going to do is just so like this angle plus this angle plus this angle is 180. This angle plus this angle plus this angle is 180. This angle plus this angle plus this angle is 180. So you get these three separate equations. But then what you can do is you can add the three equations. So you add all of the angles on one side, and then you add 180 three times on the other side. So you get 180 times 3. And then you just look and see, okay, you bring all these angles together, and you just you call that angle A. You bring these two angles together, you call that angle C. You bring these two together and call that angle D. And then you're going to get, it's going to be 180 times 3 is going to be the sum of the interior angles. And so that's the idea of, if you want to, like a way of memorizing that this theorem here is that you take any polygon and you draw diagonals to where just enough diagonals to where you can break it up into this characteristic number of triangles that aren't overlapping, and you just take that you multiply 180 times however many triangles you could break it up into. That's how you can remember this theorem. So the answer here is 540 degrees. That's 180 times 3. Okay. When drawing diagonals from one vertex of a polygon of n sides, we always form n minus 2 triangles. So that's the idea. When you're drawing diagonals from one vertex of a polygon of n sides, we can always form n minus 2 triangles. Again, because you're not going to count the number of triangles you can form based on the number of diagonals. This has more than 2 diagonals. There's another diagonal. There's another diagonal, right? There's another diagonal. So the number of triangles you can break the polygon up into with diagonals is not the same as the number of diagonals. It's actually going to be, take the number of sides and subtract 2. And that's the actual number of triangles you can break it up into. We could have done this another way. We could not have done these diagonals. We could have done that, and that's it. So we could have done these 3 triangles, right? You could. There's multiple ways you could break it up into triangles, but it's no matter how you do it, to create the non-overlapping triangles, it's going to be the number is going to be the same. It's going to you can break it up into the number of sides minus 2 triangles, and then again, once you know the number of triangles you can break it up into, you know that you can use the fact that the sum of the angles of the 3 angles of all those triangles is 180 to prove that the sum of all the interior angles of the polygon itself is equal to the number of triangles times 180. Okay. Now, note though that this proof here, this proof technique this is just for convex polygons, even though this theorem applies to concave polygons as well. Don't confuse the fact that all you remember is this convex polygon proof of the sum of the interior angles. Don't confuse that with, you think that this theorem only applies to convex polygons, not concave polygons. It also applies to concave polygons. Okay. Find the sum of the measures of the interior angles of a hexagon. Then find the measure of each interior angle of an equal angular hexagon. So, Okay, how many triangles can you break up a hexagon into? Well, hexagon is 5. Or no, hexagon is 6. Pentagon is 5, hexagon is 6. So you can break up a 6-sided hexagon into 6 minus 2, 4 triangles. So 4 times 180. And just note, that's the, if we come back to the theorem, that's the formula, right? In essence, this formula is saying you take n minus 2, the number of sides minus 2, that's telling you how many triangles you can break it up into, and then just multiply that times 180. Okay, so 4 times 180 is 720. Now find the measure of each interior angle of an equal angular hexagon. Well, 720 divided by, there's going to be 6 vertices. So 120 degrees. Find the number of sides in a polygon whose sum of measures for its interior angles is 2,160. So, okay, how many sides does this polygon have? Okay, well, n minus 2 times 180 is going to be 2,160. So what is 2,160 divided by 180? $360. Okay, so that means that n minus 2 is equal to 12, so n is going to be equal to 14. So this is a 14-sided polygon. Okay, now, regular polygons. A regular polygon is typically what we think about when we think of a polygon. So like a stop sign, that's an octagon, but it's technically in a subcategory of octagons called regular octagons. So, okay, on page 98, the next page, the figure shows polygons that are, respectively, so one is equilateral, one is equiangular, and one is regular, which means that both sides and angles are congruent. Note the dashes that indicate congruent sides and the arcs that indicate congruent angles. Okay, so let's take a look here. So the first figure they said this was equilateral, meaning all of the sides are congruent or of equal length. And note they show congruence with these dashes like this. You'll get used to this convention as we go through the course. But this is not equiangular. We can clearly see like these two angles are different. Okay, now, but this is a polygon though, right? It's a closed planar figure with lines for sides, line segments for sides, and they only intersect at the endpoints. Okay, here, this is equiangular polygon. All the angles are equal, but we can see like this side length is shorter than this side length, so it's not equilateral. Okay, now, but here, this is both equiangular and equilateral, which means that it falls under the category of being a regular polygon. This is a regular pentagon. Okay, so definition, a regular polygon is a polygon that is both equilateral and equiangular. Now, you might wonder, well, can a concave polygon be regular? Well, no. And the reason, if you think about it, is because a concave polygon is going to have at least one interior angle be a reflex angle. Well, then how could all of the angles of a polygon be reflex? So in this case, it's not by definition that a concave polygon is not regular. It's just not possible. All right, so the polygon above, the third polygon, is a regular pentagon. Other examples of regular polygons include the equilateral triangle and the square. In Chapter 3, we will prove that any equilateral triangle is also equiangular. So, yeah, you can see they just mentioned here that the equilateral triangle was regular. They didn't mention equilateral and equiangular because the reason is because if a triangle is equilateral, it must be equiangular, which means that since the angles sum to 180, it's going to have 60-degree angles. And the square, just by definition, you can imagine it's also going to be regular because the square has equal side lengths, but it also has, it's like the sides are perpendicular to each other, so it forces equiangular and equilateral by definition. Okay, based upon the formula for the sum of the interior angles of a polygon from the previous theorem, there's also a formula for the measure of each interior angle of a regular polygon having n sides. It applies to equal angular polygons as well. So this is going to be a corollary of the previous theorem for the sum of the interior angles of a polygon. And all this is that this is a formula for the interior angles of a regular polygon. And it's really kind of trivial. All they're doing is they're taking this formula and dividing by n, the number of sides. Why? Because the number of angles is equal to the number of sides. And since the number of angles is equal, or since the measure of the angles are equal, then you just take the total sum of the interior angles and divide it by n, right? And it says that this formula applies to equal angular polygons as well. So if we come here, you can use this formula for not just regular polygons, but equal angular polygons. They don't have to be equilateral. And that makes sense because this theorem that this corollary is based on, this sum of the interior angles of a polygon, is just based on angle measure. So if the idea is it really has nothing to do with the side lengths at all being equal or not. It's just the fact that the angles are equal. If you know all of the angles of a polygon are the same measure, and you have a formula that can give you the sum of the interior angles of any polygon, no matter if it's equal angular or not, then you just, if you know it's equal angular, you just take this and divide it by the number of angles, which is the number of side lengths. So yeah, that's a corollary for the angle measure of a equal angular or regular polygon. Okay, so now they work a couple of example problems here. These are pretty simple, but in the next video, we'll work examples. You'll get a feel for this. So in this problem, you find the measure of each interior angle of ceramic floor tiles in the shape of an equal angular octagon, right? And then here you have each interior angle of a certain regular polygon has a measure of 144 degrees. Find the number of its sides and identify the type of polygon it is. So yeah, it's pretty straightforward, but we'll still work some examples like this in the next video, the example problem video. Okay, a second corollary to the theorem, the sum of the interior angles theorem, concerns the sum of the interior angles of any quadrilateral. For the proof, we simply let n is equal to 4 in the formula, the sum of the interior angles formula. Then you get the sum of the interior angles in a quadrilateral is 360 degrees. Yeah, we proved this actually in the previous example problem video. It's just like the proof that they did on the previous page with the pentagon, same idea, but you don't even have to prove it. They just use the formula. So the sum of the measures of the 4 interior angles of a quadrilateral is 360 degrees. Any quadrilateral. That actually includes both concave and convex. So yeah, just FYI, we're not talking about regular quadrilaterals here. This is any quadrilateral, concave, convex, non-equal sides, whatever. On the basis of this corollary, it is clearly the case that each interior angle of a square or rectangle measures 90 degrees. Because by definition, these shapes are equal angular. So you just take 360 and you divide it by 4. The following interesting corollary to the sum of the interior angles of a polygon theorem can be established through algebra. Okay, the sum of the measures of the exterior angles of a polygon, one at each vertex, is 360 degrees. Interesting. Okay, so now they give the algebraic proof here, but you know, I find this section kind of confusing because they're not saying they're not explicitly saying when they're referring to just regular polygons or convex polygons or concave polygons. But if we think about this, so, okay, this looks like it's definitely not regular. So now what they're saying is that, so we know that each vertex, associated with each vertex, is 2 exterior angles. So here we can virtually extend this side out here, and there's another exterior angle right there, which we can see that those 2 exterior angles, they're vertical angles, they're congruent. So now, is it the case that all exterior angles, or like the pair of exterior angles at a vertex of any polygon, are congruent? We didn't say that officially, but my guess would be yes. Let's try a triangle here. So we can do, let's see. Okay, yeah, those look, yeah, that's vertical. Those two are vertical angles. But then we can also see from the standpoint of that, like, this interior angle is supplementary with this angle, and it's also supplementary with this angle, so they have to be, we didn't change this angle. And same thing here. This interior angle is supplementary with this. It's also supplementary with this. So we haven't proven it officially, but you could say that the pair of exterior angles at each vertex of any kind of polygon are going to be congruent. Not exterior angles at different vertices. I mean, maybe with a regular polygon that would be the case, but for just a general polygon, like these two exterior angles are not congruent, just the pair at a polygon. And actually, let's take a look at a concave polygon. So let's see. We can do, I mean, these wouldn't be exterior angles. I guess it's kind of confusing. But yeah, I mean, same idea. These two angles are vertical angles. So, okay. But, so what they're saying is that you can take the, so you pick one exterior angle at each vertex. Just pick whatever one, they're the same measure, right? Just pick one. And if you sum them all up, sum one from each vertex all up, all the exterior angles for any polygon, no matter how many sides, it's always going to be 360 degrees. That's what this is saying. Okay. So now, again, I believe, we haven't proven it yet, but I believe if you have a regular polygon, that the exterior angles are going to be, actually, that is going to be the case. I can think about it intuitively, but the exterior angles are going to be all congruent. Like this is going to be congruent to this, but for just a general polygon, no, that's not the case. It's only these pairs at the same vertex that are congruent. Okay, so let's look at the proof. A polygon of n sides has n interior angles and n exterior angles if just one of the exterior angles is considered at each vertex. As shown in this figure here, these interior and exterior angles may be grouped into pairs of supplementary angles, such as angles 1 and 1 prime. Okay, because there are n pairs of angles, the sum of the measures of all pairs is 180 times n degrees. So yeah, what they're saying is you can group each for each exterior angle, you can group that with the interior angle they're supplementary pairs, and so you can, since you know that what you could do is you can say that the sum of this angle plus 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 this angle all the way around is going to be 180 times the number of sides, or which is the same as the number of vertices. Okay, now it says, of course, the sum of the measures of the interior angles is this. Okay, so in words, we have the sum of the measures of the interior angles plus the sum of the measures of the exterior angles equals the sum of the measures of all supplementary pairs. Oh, yeah, cool. So what they're going to do now is we're going to solve this for the sum of the measures of the exterior angles, right? So they're going to subtract, we have the sum of the measures of all the supplementary pairs is 180 times n. So they subtract this n, but the sum of the measures of the interior angles is this. So they subtract that from both sides, and the n actually subtracts out the 180 times n. So you don't have the n anymore. You're just left with s is equal to 360 for any kind of polygon. Interesting. So now, so that's for sure works for any convex polygon. I'm just curious about a concave polygon. So it looks like it's going to be the same thing. So you would have like that. Well, I think you don't have the only thing is you don't really have an exterior angle at the reflex angle of a concave polygon. So maybe this is kind of that doesn't apply here, but it should be the same idea if you treat this like it's an exterior angle. Well, no, this isn't an exterior angle, because how are you going to relate this angle as like a supplementary pair with, yeah, so I would say with a concave polygon, you don't have at the reflex angle, there is no exterior angle. I mean, unless you consider, well, no, I guess this would be the exterior angle. So yeah, that's kind of confusing. So just think about this idea with, think about this corollary with convex polygons. Okay. So now another corollary, which it says follows from the corollary we just proved, is, okay, so the measure E of each exterior angle of a regular polygon or equal angular polygon of sides n of n sides is 360 divided by n. Yeah, exactly. So it makes sense that an equal angular or regular polygon is going to all the exterior angles are going to be the same. They're all going to be the same, not the same as the interior angles. They're all going to be the same as each other, right? An equal angular polygon, all the interior angles are the same measure, but all the exterior angles are going to be the same measure as well. So all you do is just take 360 and divide by the number of sides. Okay, so here they do an example. Find the number of sides of a regular polygon if each interior angle measures 144 degrees. Okay, so they want us to use that corollary we just talked about to solve this. So, okay, well, we know that we saw that the interior angle is going to be supplementary with the exterior angle. So 180 minus 146 is going to be 34 degrees. Or no, it was 1 minus 144. So each exterior angle measures 36 degrees, but we know it's a regular polygon. So, and the sum of all the exterior angles is 360. So you just divide 360 by 36. That's going to be 10. Right? 360 divided by n is going to be 36. So it's going to be, n is going to be 10. 10 sides. Okay, polygrams. A polygram is the star-shaped figure that results when the sides of convex polygons with 5 or more sides are extended. Okay, so again, a polygram is the star-shaped figure that results when what? When the sides of convex polygons, so convex polygons with 5 or more sides, so not 4 sides or like a triangle. You can't do this with a triangle or a quadrilateral, but anything bigger than pentagon or bigger, and those sides are extended. So, okay, when the polygon is regular, the resulting polygram is also regular. That is, the interior acute angles are congruent. The interior reflex angles are congruent, and all sides are congruent. Okay, the names of polygrams come from the names of the polygram whose sides are extended. Figure 2.37 shows a pentagram, a hexagram, and an octagram with congruent angles and sides indicated. These figures are regular polygrams. So, okay, you just take there's the pentagon, right? That's a regular pentagon. And what they're saying is you extend the sides. You extend the sides until they meet. And you get this polygram, or this is a pentagram. Okay, and so here you've got, let's see, hexagram, 1, 2, 3, 4, 5, 6, and they extended the sides. And then this is an octagram. So 1, 2, 3, 4, 5, 6, 7, 8. But these are regular, though. But the idea is you could do this with any polygon, right? It doesn't have to be regular, but it has to be convex, though. You can do this with any polygon as long as it's convex and has 5 or more sides. And you just extend the sides until they meet. And you get this star-shaped figure because of these, like, the ends meet at these points, right? Okay, but with a regular polygram, the interior angles are congruent. So, like, I think what they mean by that is you don't have any, once you create the polygram, these aren't sides anymore. These dotted lines, those aren't sides anymore. They put them as dotted lines to show the foundational polygon, but those aren't sides. So these are the sides now. But the interior angles are still congruent of this polygon, because this is still a polygon, right? once you erase these sides, this is still a polygon. It's called a pentagram, but I guess technically you would, this is a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is technically like a decagon, right? Because does it meet the definition of a polygon? It's closed, it's planar, its sides are line segments, and the line segments only intersect at the endpoints of the line segments. That's the definition of a polygon. So this is a polygon, it's a decagon, but because of its where it comes from, it's the extension of the sides of a pentagon. They call it a pentagram. But what's going to happen is, since we extended the sides of a regular pentagon, the angles are going to be congruent and the sides are going to be congruent. And then it says, let's see, the interior angles are congruent and the interior reflex angles are congruent. So what they're talking about there is these interior reflex angles are all congruent as well. Okay, and so with congruent angles and sides indicated, these figures are regular polygrams. All right, let's work some example problems.